Welcome everyone. I know I'm the last thing standing between lunch and you, so I will try to keep it rolling, keep it digestible, and keep it quick. Now, today I'll be talking about SBI 3.0, and I'm Atish. I work for Rivos, and my co-presenter Anup couldn't make it here, so I'll be presenting the set of slides talking about SBI 3.0. Now, brief introduction on SBI. Just wanted to get the feel of the room. How many of you here feels like deja vu? I've seen this diagram many times over last 5-6 years. Oh, I don't see many hands, so I guess I have to go through this and keep you hungry. Whoever has seen, you know whom to blame. So just a quick overview, SBI is the Supervisor Binary Interface. It's the interface that defines how does the supervisor mode software, maybe it's running like Linux kernel in S mode or Linux kernel in VS mode, talks to the higher privilege mode, which is M mode in case you are running Linux bare metal, or like in case scenario, you're talking about the hypervisor. So SBI defines the interface and all the mechanism how your supervisor mode talks to the higher privilege mode. And we have been going over SBI specifications, keep it evolving over time, and then both side describes what's the interface, how does it difference between without H and with H, like virtualization. And it's basically how system calls, applications you make system calls drop into those operating systems. Operating system makes the SBI calls, which is technically in the instruction is an eCall, drops to the higher privilege mode. Now, here's a brief history of SBI timeline. So we released 0.1 in 2019 when I was young and optimistic. By the time in 2021, we released 0.3 when I had a newborn at home. Now here we are, 2025, we released 3.0 with a lot more gray hair, with a 4-year-old at home, keeping me busy. So you'd see we just have more acronyms, aka extensions in SBI, but we'll go over why we need it, why it keeps evolving, and then what's new in SBI 3.0. So typically, if you look at SBI, it tries to address different extensions, try to address different problems. So one is always been a little bit of contentious is to bridge the ISA gap. Sometimes ISA doesn't provide enough infrastructure to access these features in supervisor mode or where your typically Linux kernel runs. So we have to define the SBI extension just to bridge that ISA gap. In the past, Jeff talked about the performance monitoring. That was one of the big use case to bridge that ISA gap. Now it's the debug trigger extensions. Because the debug trigger extension is only accessible in firmware mode or M mode, we have debug trigger extension to SBI debug trigger extension to exercise that from kernel mode. Then we need higher privilege mode assistance. That means kernel needs some feature information or enablement from firmware, supervisor mode software requires firmware assistance. That's why we have firmware feature and supervisor SSE event. And then I'll go over the system abstraction, which is a little bit new extension, which has a broader scope beyond what you have been seeing mostly in the core. Now, let's go over the supervisor software events. So what is SSE? So supervisor software events is software-defined events that can be injected by the higher privilege mode to the lower privilege mode. That means your M mode or your hypervisor or firmware running in M mode or hypervisor running in HS mode can inject events to Linux kernel or any supervisor mode software running in the lower privilege mode such as S or VS mode. Now, it can preempt any other traps or interrupts. It's really powerful. And it can also has preemption between the events. So event has the priority. So if the supervisor mode software handling a lower priority event and higher priority event comes in, it can preempt that as well. And then it supports your local per CPU and global events. I'll go over why we need it. Now, it has a straight transition that goes from unused where it's defined, implemented, but supervisor mode software is not using it, which is absolutely fine. It all depends on the implementation, to register when the supervisor mode software actually register for the event, saying that now the higher privilege mode software knows that this event is in register state and I should serve this, but not until supervisor tells explicitly saying, hey, I'm enabling this event. Now you can give me the events based on what hardware feature that event enables. Now, SSE events can, remember, it can interrupt anything. It can interrupt S mode at any time, even if the interrupts are disabled. So why we need such a powerful mechanism for firmware to interrupt SSE? Particularly two use cases. One is RAS. So RAS is always, in RISC-V philosophy, we have adopted firmware first. So firmware is the one who gets the RAS errors or like RAS interrupts, and then it has to update the RAS records and then go and notify the kernel saying that, hey, the RAS error happened. And then that has to happen as soon as possible, as fast as possible, and we cannot rely on saying, hey, interrupt is disabled, now I cannot handle the RAS interrupt until a RAS event until the interrupt is enabled. So that's one key use case. Another is PMU overflow interrupt. So PMU overflow is basically when you're doing puff sampling, what you have to do is actually there is an overflow interrupt that happens when a particular, whatever the sample rate you configure, that expires, and then that overflow interrupt is a local interrupt. So when you are doing profiling, if you are using user space profiling, doesn't matter. But if you are monitoring, trying to profile kernel and you have a lot of blind spots when kernel runs with interrupt disabled, that's when SSE comes into picture, and then SSE can avoid those blind spots and give you an profiling data of what's kernel running. And that these two features were defined in SBI 3.0. And it's not like anybody can implement any event that can go into the Linux upstream. It gets reviewed in the PRSTG, and then eventually it gets adopted if there is a genuine use case. So recently there was proposed and being discussion been happening with NMI triggers, and then in the past there were discussions, but it didn't pan out in patches, so we have not taken it, is the parameterized asynchronous space faults. Now, what's the software ecosystem status? So spec is ratified. We can now merge these patches into the kernel or OpenSBI implementation. So OpenSBI implementation has been available since 1.7. Linux upstream patches are in progress, so anybody wants to review, please welcome. KVM implementation also is proof of concept is available. And then KVM unit test, we have adopted KVM unit test as the standard test suite for SBI extensions. So that's already merged so that we do validate all the extensions that gets into the spec with now KVM unit test and the proof of concept. So let's move to the next extension. That's message proxy extension. Now, message proxy extension is an abstract interface to send messages from supervisor mode software to any entity in the system. I'll go over why I call to any entity in the system. It's protocol agnostic, and it in this picture, I have described a little bit of RPMI, which is RISC-V platform interface, platform management interface, specifically because at this point, only RPMI is the only message protocol that's defined to support over MPXY, but you can extend it for any vendor-specific message protocol or any standard messaging protocol that we may come up with in the future. Now, it's based on per-heart shared memory, and then the messaging format, again, since it's an abstract interface, it doesn't define the format. The format it gets defined by the messaging protocol. Now, what exactly it does, how does it exactly work? So this is a typical software ecosystem, let's say in your platform. So you have non-secure world where your UEFI, EDK2 is just an example, your UEFI firmware, UEFI mode runtime services runs, your Linux kernel runs, and then on the secure world there is supervisor mode, and there is a platform controller doing, let's say, clock management, voltage management, or sensor management, anything for that matter. And if your CPU needs to talk to that, and then your kernel needs to invoke that, that's where MPXY comes into picture. MPXY handles, forwards that message to the M mode. M mode now forwards that message packed in RPMI to directly the platform controller, and then vice versa. And MPXY provides different supports for notifications via SSE or MSIs, which can be leveraged. and then you can define a full messaging kind of IPC between your CPU and any of the remote microcontroller that you may have. So what it does, the remote entity can be remote processor. Also, a remote entity can be just an M mode firmware. You don't need to talk to a remote controller. What you want is the message needs to be delivered to the firmware to do a certain operation, and then firmware may do it by itself, or firmware may also invoke another supervisor mode software, which is I was showing as the secure mode software, or depending on the platform implementation. But it can pass that message so that it gets executed in a separate supervisor domain that it can execute. What are the examples? What are the advantages we have? We get a lot of platform abstractions. So for example, we have now a generic clock driver. So anybody who is using this don't have to develop upstream their Linux kernel clock driver. If they support the clock driver via MPXY and RPMI, they get a generic clock driver across generations. You don't have to bother about upstreaming that driver or new changes, because it's all hidden behind the firmware and your clock controller. Now, that may not be the philosophy that you want. You want a, let's say, 2 upstream on every revision. That's also well and good. I'm running a little bit of time, so a little bit hurry up. So the next use case that we have is EDK2 standalone MM. The couple of use cases here is the RAS error table and secure variable updates. So both of the case, Linux kernel makes an UFI runtime call to the EDK2. EDK2 for the secure variable, Linux kernel makes an runtime services call to EDK2. EDK2 makes an MPXY call to the M mode, and then M mode sends forwards that message via request forward group to the EDK2 MM, which is running in the secure mode. For the RAS variable updates, same goes. UFI invokes M mode, and then it gets executed on the other side with the secure vault. And M mode does the context switching. M mode is responsible for context switching between these two. Both of these use cases uses different channels. So channel is basically a virtualized pipe between this non-secure world to the secure world, or non-secure world to the M mode, depending on where you are drawing the abstractions. Now, the other use case is Opti. It's all these use cases have been evolving, and then the POCs are available. So Opti also, your OptiSys driver, Linux kernel driver, talk to the Opti driver that's present in the Linux kernel. It makes an MPXY call. Linux kernel OpenSBI, which is a POC, is done for Opti, does the context switch, goes back to the Opti OS, and then the messaging format again here is either you can have an Opti service group of RPMI within this, or you can define your own service group. That thing is being worked on. Now, the ecosystem updates, M mode implementation available already from again OpenSBI 1.7. Linux kernel implementation just got merged. You know what happened on 6.17. So 8.rc, finally these patches got merged with mailbox controller and system MSI drivers. And then all other POCs are available and eventually land in respective upstream projects. Now next is the firmware feature interface. So firmware feature interface allows supervisor mode software to control the hardware and firmware specific features. Why we need it, or what's the advantages? Sometimes it's the ISA that mandates it. Sometimes it's the firmware. We want to have a roll out features easily and have a backward compatibility while we are rolling out the features in the Linux kernel. For example, we used to have misaligned aligned delegation exception handling in M mode in OpenSBI. Now we want to do it in kernel, but then we have to manage the backward compatibility. So we enable it through firmware feature. Similarly, these features are can be local or global. So when I say local, it's per CPU, you enable it on every heart. So for example, there are features such as landing pad shadow stack, which is CFI related. These are our hardware ADUB update. These are actually CSRs that need to be updated, so it has to be per CPU. While misaligned exception, it can be a global feature, because for the entire firmware, you just need to, you are controlling a firmware feature rather than a hardware feature. Depending on the use case, you define those features. Now, again, ecosystem updates, all of them have been merged, except the KVM one, which has got recently merged. Now, last one, the debug trigger. As I said, it's an ISA gap that it's the specification addresses. So it addresses the native debugging. It allows the native debugging using hardware breakpoints. And you might have used remote GDB with the software breakpoints. It allows the next iteration with hardware breakpoints. And then it allows privilege mode to share the debug triggers, and then the specification allows specifically with enumeration and configuration of debug triggers, and then it's based again on the shared memory. So a lot of this takes inspiration from the previous iterations where you take the shared memory, use the shared memory, create a para-virtualized interface between your lower privilege mode and higher privilege mode, and then you go through it, you use that to pass information between the privilege modes. So again, software ecosystem status, the Linux kernel implementation, particularly for debug trigger, the POC is available. I think we are on V1 or V2. There is lot more things need to be done, but it's based on perf, and then it's both support hardware breakpoint and watchpoint. KVM is not done. It's much bigger. The scope is much bigger compared to other extensions, so slowly the patches are trickling in. The OpenSBI patches have been merged, and then KVM unit test also recently merged in upstream. And then any of the things you see TBD, if anybody is willing to contribute to the patches or take up something like this, please, you're welcome to do that. Now, as humanity evolves, we have to evolve, keep evolving. So there will be an SBI 4.0. This will be not the last talk about SBI. I guarantee that. So what do we do? What is the future plan for SBI 4.0? We have a couple of extensions that being discussed on the mailing list, such as para-virtualization lock to efficiently manage spin locks in the guest, and then have a much more optimized version of it. Then there are more improvements coming for MPXY, specifically for TPM 2.0, or if any of the RPMI messages require MPXY, any improvement in MPXY that will land in. Obviously, we'll have new firmware features that I discussed, like NMI triggers, or any features that we eventually discover in next year or so. Then we discussed this little bit about the PRIP software SE update, watchdog extensions, and then obviously one of the big one is confidential computing, which has a whole suite of extensions and a lot of APIs. So that will take its own course time, but hopefully all these will package it in 4.0, and then whenever it's ready for ratification, we'll go through the process to ratify it, and that's what we'll have in SBI 4.0. And then sometimes what happens is these are the things we have planned right now. As next year rolls out, we may have more request features or like a different extension. We'll include that as we see fit in the ecosystem that actually helps the ecosystem, rather than just anybody request any SBI extension that we got added. Okay, so that's all I have. Any questions I can answer?